Well, good evening. Welcome to AP Live. Tonight, my name is Roger Siegel, and I'm broadcasting from Sarasota, Florida. And we are tonight continuing with our study of AP Physics C, Electricity and Magnetism, and we're helping you guys get ready for your exam that's now less than 2 weeks away. So that's really exciting. I hope you're getting ready. And with me tonight, as always, is my friend and colleague, Kristen. Hi, Kristen.
Hi, how are you, Roger? I am Kristen Gonzalez Vega, and I teach in Frisco, Texas at Reedy High School.
Okay, great. So if it's your first night with us, welcome. We're glad you joined us. If you're back, welcome back. Glad you came back. And as I said, we're continuing along. The exam's coming up real soon. I hope you've been reading your emails. My young students, please read your emails from the AP because there's a lot of important stuff that came our way just yesterday in an email. And specifically, I'm talking about the 51-page PDF that you got, all about testing procedure, which is so different than any way it's been done in the past. So please, if you're not hearing it from your teacher, you got to find it on your own. You can find it, but the information is there. It's important. We'll talk more about it as we get closer to the test, but we want you guys to start getting ready. Also, well, let's go ahead and continue on. I'm going to find my screen here. And okay, here we go. Oh, I didn't do that. I need to share my screen. And so first let me share. Okay, there we go. And so here's my deck, and I'm going to go through this. So today is our 19th day of review. Welcome, Thursday night. And today we're going to continue with steady state, but we're also we're going to introduce the capacitor tonight. So that's going to be different. Again, my name is Roger Siegel, coming to you from Sarasota, Florida, joined by Kristen in Frisco, Texas. Remember that your exam is going to be on Monday this year, and depending on where you live is going to dictate what time of day you're going to take the exam, because the exam is given at the exact same time all around the world this year, since you're taking it from home. So I teach in the Eastern time, so my kids are going to take it at 2 p.m. And I know we have students from all over the world, so make sure you're in communication and finding out when your exams are going to be. Again, this year we're going to have 2 questions, a 25-minute question to read and 5 minutes to upload, and then a 15-minute question to read and 5 minutes to upload. Again, I really want you to delve into that PDF that got sent out yesterday. It explains everything about the exam that you need to know. All right, so here we are this week, and as I said, we are actually going to push a little bit ahead with our capacitors today, and the reason for that is I almost forgot to tell you, we have a special guest tomorrow night, and I'll tell you more about that later. It's going to be a lot of fun. But we are finishing up the curriculum. Tonight and tomorrow night are our last nights where we're reviewing everything, and the units that we're reviewing are 1, 2, and 3. 4 and 5 are not going to be tested this year. And starting next week, we're going to start giving you problems to work on. And so we're going to give you basically some mock exams next week. All right. But today we are going to talk about these transient circuit conditions, the transient circuit conditions, things that are changing. RC stands for resistor capacitor, and that's what we're going to study. Calculate the time constant of a circuit containing resistors and capacitors arranged in series, and derive expressions using calculus, ladies and gentlemen. Yes, it's exciting. Tonight we're going to use calculus to describe the time dependence of the stored charge or potential difference across the capacitor, or the current or potential difference across the capacitor, the resistor in an RC circuit when charging or discharging a capacitor. Okay, so I need to talk a little bit about how a capacitor behaves, and I'm going to start talking a little faster because I have a lot to cover tonight. So we're going to start with the battery here. This is what's called an RC circuit. And we say behaves as it charges. So we're going to start with no charge, 0. I'm going to say at t equals 0, Q is equal to 0. There's no charge on the capacitor. And so a battery sends out charges, pushes charges, and it pushes the charges that are in this wire. Just by pushing on this one, it pushes on these. And it pushes a positive charge onto this side, which then creates a negative charge. Well, that creates a little, almost like a little battery here. It creates a voltage drop here. And so as the battery puts more charge on here, guess what? That voltage goes up. And as the battery puts more charge on here, we keep making it harder and harder. It'll keep increasing the charge until these two are the same, until the potential across the capacitor is equal to the potential across of the battery. And so we're going to now derive the time-dependent current equation. This is one of my favorite things to derive, so this should be a lot of fun. All right, so we start with E, R, and C, and we're going to close our switch. And so now I'm going to analyze this using Kirchhoff's loop rule. I'm going to start with the voltage gain across the battery minus the voltage drop across the resistor minus the voltage drop across the capacitor equals 0. Now, the voltage drop across the resistor is IR. The voltage drop across the capacitor is Q over C, and so that's equal to 0. But you remember that I, current, is equal to dQ dt. And so let's go ahead and put that in there. And so now E is equal minus dQ dt times R minus Q over C is equal to 0. Now, looking at this, it might look intimidating, but there's only there's an independent variable, a dependent variable, and 2 constants. So we should be able to solve it, and we can. So first thing I'm going to do is I'm going to get the differential on the other side, just to be able to kind of survey the terrain here and see what I've got. I'll bring the R along with it. And so from experience, I know this is going to be easier if I put a common denominator. So I'm going to say EC minus Q all over C, and that's going to be equal to dQ dt times R. And now I'm going to bring the C to the other side, and so I'll get EC minus Q is equal to dQ dt over C. I'm sorry, times RC. And it looks like I wrote dd dt, and that's incorrect. All right. Now, I'm going to do some algebra in order to be able to separate the variables. And so I'll end up with a dq over EC minus Q. And on this side, I'll end up with a dt all over RC. And you can go back and check my algebra if you want. Now, the next step in solving a differential equation is to integrate both sides. So we'll do that. We're going to say dq over EC minus Q is equal to the integral of dt over RC. All right, now on the left, you might recognize this as a logarithm. And so this is going to be the negative logarithm of EC minus Q. And on the right, we're going to get just T over RC. And just like you learned in calculus, never forget the constant. Now in this problem, at t equals 0, Q is equal to 0. So I'm going to say minus ln of EC is equal to C. So now I have enough information here to be able to put that back in and try and solve this for Q. So I'm going to put the C in here. I'm going to continue up here, and I'll write my equation. So I have a negative natural log of EC minus Q is equal to T over RC minus ln of EC. Now, I can bring the logs to one side to try and isolate them and then exponentiate to get the Q. And so I'm going to have a positive ln of EC minus Q minus ln of EC is equal to, and over here on the right, I'm going to have negative T over RC. Now on my left, you might recognize this as a quotient. I can write that as the difference of, the quotient of EC minus Q, the natural logarithm, over EC. And what that allows me to do is to exponentiate both sides to the base E. So I'm going to say E, and all of this, E raised to all of this, ln of EC minus Q over EC is equal to E raised to this power T over RC. Now on the left, you know why I did that. That was to get rid of the logarithm. And so what I'm left with over here on the left is EC minus Q over EC. And on the right, I've got E minus to the minus T over RC. Now I'm still trying to solve for Q, and I'm a few steps away. You can probably see it coming. EC minus Q is equal to EC times the exponential to the negative T over RC. And so I have a negative Q is equal to a negative EC plus EC exponential to the minus T over RC. And my final step gets me to Q is equal to the quantity EC, quantity 1 minus E to the negative T over RC. Now let's kind of pause and catch our breaths there for a minute, because that was a lot of math. I timed that before and it was way over 5 minutes. Now, look at this derivation. I'm not going to harp on the derivation much because I think it's kind of like memorizing a poem or a dialogue in a foreign language class. You practice it a few times and you get really good at it. But what I want to look into and really focus on is this function. This is the charge on the capacitor as a function of time. Now, you might have seen this elsewhere. You know, this is a very common form, and what I'm talking about is it's called an exponential approach. And so when we have the form of Q is equal to a constant K times 1 minus E to the minus another constant rho T, that what that's going to give us is that's going to give us what's called an exponential approach. Okay, and so that value is going to be K. So here what we have is we have the charge increasing and exponentially approaching some value that is E times C. And remember, that's our formula for Q for a capacitor is EC. Now that gives us the charge, but if I'm building an amplifier, it's very hard to measure the charge. I need to measure something like the current or the voltage. And so we can do that because once we've done the heavy lifting, the differential equation that gets us the charge, there's only 2 or 3 steps away to the current and the voltage. So first, let's find the voltage. That's the easiest one. The voltage is equal to Q over C. And so we're going to take this and divide it by C, and we have E times 1, the quantity 1 minus E to the negative T over RC. And so that one is a fun and easy one. That one you don't lose any sleep over. The next one does take a little skill. What is current? What is current? We've already said that current is dq dt. That's how we got to the differential equation in the first place. And so let's take the derivative d dt, and I'm going to go ahead and multiply through the EC to make it a little easier for us. And that's going to be EC minus EC e to the minus T over RC. All right, now, what is that? Well, the derivative of the first term is 0 because that's a constant. But the derivative of the second term, we're going to leave the negative EC, and then we're going to take, what's the derivative of e to the u? It's u prime e to the u. So the derivative of this, negative t over rc, is negative 1 over rc times e to the u, e to the minus t over RC. And so the EC, the C cancels, and so the negative cancels, and so we have I is equal to V over R times E to the minus T over RC. And this, ladies and gentlemen, our final formula, that is an exponential decay. And so let's take a minute and come down over here and see what this looks like. We've got the time-dependent capacitor charging equations, and these are the ones that we have in front of us. We derived this one with the heavy lifting of solving the differential equation. For this one, we just divided Q by C, and for this one, we took the derivative. And let's draw these out, and let's hopefully understand why they make sense. So once again, the charge increases exponentially. That's Q as a function of t, and this value right here is EC. All right, my current is an exponential decay, and we have I here, and the value here is, look at that, my constant here in front is E over R. Well, ladies and gentlemen, that is Ohm's law. I is equal to E over R. And so remember, at first, the capacitor acts like a closed switch the instant that it's closed. And so that instantaneous first current pretends like there's no capacitor. And so that's why we get E over C, and this is a function of time. And finally, the voltage down here. And I want you to think about this too. What's happening? Remember what we said before, that our voltage, this is our voltage across the capacitor, and the value that it's approaching is the EMF exponentially as a function of time. And why is that? Well, remember what we were saying here is that this voltage gets bigger and bigger and bigger until it equals this, until these two, the left and the right, balance out. They both are pushing, or they both are equally of high potential, and so we have no more current flowing. Now, there's one more thing that we want to look at before we try some problems, and that is the time constant, okay? And so the time constant is this RC. You can see it in all of these, T over RC, T over RC, T over RC. Now let's say, see what that means. If we go one time constant over here, I'm going to just put this. This is T is equal to RC. That's one time constant. If I go up here and I come over here, well, what is that value? Well, this value is 1 minus e to the minus 1. Okay, and that comes out to be about 0.632. Okay, about 63%. So after one time constant, the charge has gone to 63% maximum. Let's look at the time constant here under exponential decay. Okay, here would be my RC, and that's my tau, time constant, is equal to RC. And when I come up here, here's what I say, and this is not to scale, please. So is going to be the 1 minus this value. So this is 0.368. And what we have there is that is e to the minus 1. So that's what my time constant can tell me. Now, this goes up very quickly because it's an exponential. So after 2 time constants, we're up into the high 90th percentiles. Most people will say to totally charge, you only have to wait 5 time constants, or to totally decay, you only have to wait 5 time constants, and you get to 0.99999, something like that. But that's kind of where we are. So we want you more than the math, and I had to do the math just because it's part of the curriculum, but more than, and I really wanted to be honest, but more than the math, we really want you to think about why these graphs are shaped the way they are. If you can do that, if you could, with your friends, sit down and say, well, this graph is shaped like this because of this, and relate it back to this picture and what's going on, that's what's going to be really key to being successful on this year's exam. Not so much the math, but really understanding what's behind it. Okay. So anyway, Kristen's got some great problems for us. And so she's going to do a few. And Kristen, I think your problems tonight are going to take longer than mine. So I'm only going to need about less than 10 minutes at the end. So don't feel like you got to give me 15 minutes. All right.
Okay. All right.
All right.
I'll try to talk slowly then, and maybe
You
we'll
don't
throw
have
in
to.
some other
We can
things.
let them go early if we need to. Okay.
Okay. So we're going to look at a problem. And I want to say that, like we've been talking about, it's important to conceptually understand these. And I think that this would be something, if you are making a short list of things that you're trying to have ready for the exam, is that you will not be asked to do this derivation on the exam, but it's very possible that you may have to analyze a situation where you do have a capacitor that is charging or discharging. So having these relationships already worked out somewhere, I think is something that you could do and have ready, because you're not going to have to derive it, but you do have to understand how to derive it, because you could still be asked about a capacitor that's charging or discharging. Maybe you're given the equation and you're asked to explain what is going on, or maybe you're given a graph and asked to create a circuit of what that graph could look like. So it is important to know that derivation. Even this year, you won't be typing that in the problem, but you can absolutely be applying it. So we've got one here where we are actually have a circuit. We have one resistor that has a resistance of 50 kiloohms. We have a switch. We have a power source that has a potential difference V naught across it, and we have our capacitor C in our circuit, right? So we have our one series circuit here. And we're an engineering firm that has built the circuit, and the current is measured for the time after the switch is closed at T0, and the best fit curve is represented by the equation. I, as a function of time, is equal to 5.2 e to the negative t over 10, where I is in milliamps and t is in seconds. So we want to determine the value of the charging voltage predicted by the equation. So what would that charging voltage V naught be given this equation? So we want to look at, well, what do we know? So we have our equation, and I'm going to rewrite it over here so we can talk about it. I is equal to, and really, well, I'm not going to say anything just yet, 5.2 e to the negative t over 10. So let's look at that equation that Roger just gave us for current, right? So he said that after we derived that charge as a function of time, and then we took the derivative of that, and we got our current equation, we got that I as a function of time is equal to E over R times e to the negative t over RC. And this holds true for any capacitor that is charging. So we can look at what they give us, and let's see what kind of these things mean. So if I look at the first part here, this E over R in front of our E, well, what does that correspond to? That corresponds to our 5.2. Well, what is E over R? That is our initial current, right? Because if we look at that and we go back to our equation here, if I were to put 0 in for my t, well, what is e to the 0 power? Well, that's 1. So this would become 1, and I'd be left with just ER. So the current at time 0 is just equal to E over R. And this is through the resistor. Okay, so when we write these equations, this is for the current through the resistor as a function of time. Well, this is the voltage source. This is the resistance of the resistor. And so that means that all of that current from the battery is going through that resistor at time 0, because there's no charge on our capacitor. So that is why we can say our capacitor acts like a wire or a closed switch at time 0, because we can use that equation and prove it. So if I look here and I look at that equation, and then we can also look at RC, and I have that 10 is RC. So those are the kinds of things I'd be thinking about when I'm given this function. I know that my tau, my charge constant, is equal to 10, which is equal to RC. And I also know that my E over R, which is equal to my initial current, is equal to 5.2. But remember, this is saying that this is in milliamperes. So really, this would be 5.2 times 10 to the negative 3 amperes. Okay, so when you're given these questions or given these equations or graphs, before I even read the question, I'm always looking at, well, what can I know from these things, right? So what are some things that I can pull from this before I get too involved, and let's just jump in and do it. So we're going to analyze that. Okay, now we're going to look and see, well, what can we do then with this? So I want to know what the charging voltage is, right? I want to know what this potential difference V naught is. Well, I've already kind of recognized here what my initial current is. That's all going through that resistor. And so if I want to know what the potential difference is, well, I can use Ohm's law, because I know Ohm's law is equal to I times R. And so then we're simply plugging in. I already kind of know here that my I is equal to that 5.2 times 10 to the negative 3. So I can say V naught equals 5.2 times 10 to the negative 3 amperes times my resistance, which is 50 kiloohms. So that's 50 times 10 to the 3 ohms. And so if we multiply that out, we can get that that charging voltage is 260 volts. Okay. So next part, let's determine the capacitance. So what kind of relationships do we have for capacitance? There's kind of a couple of different ways that you can do this one. The easiest one I see is that I know that my tau, my constant, charging constant there, is equal to RC, and it's equal to 10. So that's probably what I would do, is I would say tau is equal to 10, which is equal to R times C, because I know what that resistance is. So then it becomes easy to find the capacitance. I'm just dividing that 10 by my resistance. So then C is going to equal 10 divided by 550 times 10 to the 3. Okay, and we get 2 times 10 to the negative 4th farads. Okay, the other way, though, we could do it, which I think is the long way, is we could use our relationship that we also know that V is equal to Q over C. So I could find what my total charge is by using that Q, right, is equal to, if we use I, is dQ over dt. Then we could take the integral of our current function and solve for what that Q is using, say, infinity. So you could take that integral, but I think the easiest thing is just to use that tau, that constant. Okay, so here's where we're going to have to put our thinking caps on and think through, and I'm going to give you some time to actually think about these questions, right? So I want you to be writing these down, your answers, and how would you respond if this was on the EP test, right? So the charging voltage is measured in the laboratory and found to be greater than predicted in part A. So we found that it should be, what was it, 720, right? Oh no, 260, sorry. So we found that it was 260. So we measure it, and it's actually going to be greater than 260 volts. So give one possible explanation for this finding and explain the implications that your answer has for the predicted value of capacitance. Okay, so why would it be higher than this, and what would it mean about our capacitance of our capacitor? So I'm going to pause for a moment here and let you think about it. Okay, so if we go back to Ohm's law and we know that V is equal to I times R. If this is actually greater than what we measure it, well, our current function is our current function. So what else could we look at? Let's look at the resistance. Well, in order for the charging voltage to be greater, what does that say about our resistance? It's actually greater. So what would make the resistance in this circuit here be greater? It's not an arrow, is it? How could we make this resistance in our circuit greater? We can't add any components. The components are the way they are right now. So that has to mean that either my wire has some resistance to it or my power supply has some internal resistance to it, right? There's got to be some added resistance coming from somewhere. And where would that come from? That would have to come from the wires itself or come from that power supply in order to increase that resistance, which would increase that potential difference. Okay, and next we want to change the circuit up. So our supervisor tells us that the charging time is too high. We want to decrease that charging time. So we can add in components now. We can add in resistors, we can add in capacitors in addition to what we originally had. So let's look at it both ways. How could I change this circuit only by adding resistors to decrease the charging time? And then how could I change this circuit only adding capacitors that would decrease the charging time? So again, I'm going to give you just a few moments here to write out what you think. So where could I put a resistor in here that's going to decrease that charging time? Well, we know that our charging time is related to our charging time constant tau, which is equal to RC. So if I want to change R, how do I change R to decrease that time? Well, that means I've got to decrease my resistance. Okay, so how could we decrease the resistance? Well, I could add a resistor in parallel with that resistor. Because remember, adding resistors in parallel will always decrease the total resistance of your circuit. So we're going to add a resistor in parallel, the world's worst speller. We're just going to say parallel to decrease R and decrease our tau. Okay, what about a capacitor? Where am I going to put a capacitor instead to decrease our charging time? So I'm not changing R anymore, but I still want to decrease that time. So I still want to decrease the overall capacitance of my circuit. So if we think back to how we combined capacitors, remember if we add a capacitor in series versus adding a capacitor in parallel, there it's the opposite rule of resistors. So capacitors in parallel, remember we just added up C1 plus C2. But when we were doing series, we had to do the inverse rule just like we do with resistors. So the opposite rule. So if I want to decrease the capacitance, well then I want to add one of these capacitors in series. So I could put a capacitor anywhere else in this circuit in series with this current one. So I could put it over here, anywhere within that circuit that's in series. Okay, so always thinking about what making changes does to your circuit and how you can apply those rules. Okay, Roger, did I take up enough time there for you to finish it up?
Yeah, I think you did. It was good. All right, very good. Thanks a lot, Kristen. All right, excellent. Well, let's go ahead and take it on home, ladies and gentlemen. And then we have one more night tomorrow night to continue. We'll do some more of these problems with capacitors. We'll throw some more circuits in there with resistors. It'll be a lot of fun. And then Monday, remember, we're going to start doing mocks. And so come ready to work with your calculator and your AP formula sheet next to you, and we're gonna really rock it. We're gonna do some of these problems. All right, let me go ahead and patch you guys back into my computer, and let's see. I want to bring up the back to my OneNote, and let's go ahead and take it back to some AP practice. All right. So here's another good one, and again, a laboratory one. So this is a more, hopefully some realism here. In the lab, you connect a resistor and a capacitor with unknown values in series with a battery of EMF. E is equal to 12 volts. You include a switch in the circuit. When the switch is closed at time t equals 0, the circuit is completed, and you measure the current through the resistor as a function of time as plotted below. A data fitting program finds that the current decays according to the equation I of t is equal to E over R, e to the minus t over 4. All right, so it asks us, using common symbols for the battery or the resistor, the capacitor, and the switch, draw the circuit that you constructed, show the circuit before the switch is closed, and include whatever other devices you need to measure the current through the resistor to obtain the plot above. Label each component in your diagram. So the common symbol for the battery are two parallel lines, one bigger than the other with a common center. Then we can put our switch, and so that's what that looks like. We can put a resistor in here, which is a zigzaggy thing. And our capacitor, it looks a little bit like a battery, except its two parallel plates have the same length. And so we're going to go ahead and put that C. This is R. This is my switch. And this is my EMF. And I think they told me that my EMF, did they? Was equal to, yes, 12 volts. Okay, so that was pretty easy. I knew that wouldn't be too tough. Now the next one says, having obtained the curve shown above, determine the value of the resistor that you placed in the circuit. All right, so how do we get the value of the resistor? Let's take a look. I'll give you a minute to think about it. We know the current, and we're also given the EMF of the battery. How are we going to find the resistor? Well, I hope the conclusion that you came to is that when we're going to look at the t is equal to 0 condition, or not t is equal to 0, but right after the switch is closed condition. And we know that right after the switch is closed, the capacitor is not impeding the current at all, and Ohm's law rules for the circuit. And so we know that E is equal to I over R. That's Ohm's law. I'm sorry, let me do that correctly. I don't know why I did that right. V, sorry. And so V is equal to IR. And what we're looking for in this case is the resistor. So R is equal to V over I, which gives me a voltage drop. We have 12 volts. And our current, look at what our current is here. I didn't cover it up. Is 0.01 amperes. And so that gives us 12,000 ohms of resistance in our resistor. So that's our first answer there, 12,000 ohms. All right, and then we're asked to find what capacitance did we insert into the circuit to give the result above. Now, this is not different from what Kristen just did. You have an easy answer and a more challenging answer, and we want you to be able to know about any of them. So since we have the current, all right, and we have some values here, we could plug them in and we could find out the time. But what's easier is to note that my time constant, tau, is equal to RC. That is equal to 4. And so that means that C is equal to 4 over R, or 4 over 12,000 ohms. And so 4 over 12,000 ohms is going to give us a value of 3.33 millifarads. That's a thousandth of a farad. And so that is another way that we can look at the time-dependent curve of a charging capacitor. So I hope you guys found that fun and useful. It was fun for us. Moving on, thanks for watching. Don't forget, tomorrow night we have a special guest joining us. Kristen, you want to, let me stop sharing my screen here. Hello, Kristen, sorry.
Yes, I'm here.
So, all right, what are we learning tomorrow night besides having a special guest?
We are going to just be doing a little bit more practice with these. So a couple more of these charging, discharging capacitors. And do we want to tell everybody who our guest is going to be, or do we want to hold them in suspense?
Well, okay, let's tell them.
Okay. If you are YouTube watchers, our guest is going to be Kyle Hill tomorrow, who is has his YouTube channel, Because Science. So, and he has some really awesome videos on there.
Yeah, and you should go online if you haven't seen his videos, watch him, because he's pretty amazing the way he can be talking about the Hulk one second, and then the next second from his back pocket he whips out, and then this research from from MIT shows, and so he's just bringing these things from everywhere in science to bear on the world of superheroes and comics, and it's amazing. So it's going to be fun. So thanks so much for joining us tonight. Don't forget, tomorrow night, more physics and a special guest, Kyle, Because Science, and we'll see you tomorrow night. Take care.